Hello everyone, my name is Dr. Helga Ingimundardóttir and I am with the School of Engineering and Natural Sciences at the University of Iceland. Today I am pleased to present our research on evolving submodels for column generation in cutting and packaging for glulam production, conducted in collaboration with Professor Thomas Philip Runarsson. Glulam production is vital for sustainable construction due to its superior strength to steel and concrete. Today, I will discuss optimizing the pressing process in glulam production to improve efficiency and reduce environmental impact. I will introduce a novel approach that combines column generation with evolutionary strategy to address the challenges in cutting and packaging processes. This method refines cutting patterns to optimize press utilization, reduce waste, and improve turnaround times. Our case study at Limtre in Iceland highlights the limitations of manual methods. Our proposed integration of column generation and evolutionary search modernizes the process and aligns it with sustainability goals. Next, I will explain our methods in the integration of these techniques and the improvements they bring to glulam production. The pressing process at Limtre faces challenges due to integrating old and new machinery. Our mathematical model addresses these optimization press allocation to minimize the presses needed. Additionally, our model focuses on reducing waste, as shown in red on the press configuration diagram. This involves the optimal assignment of beam items across all presses to ensure efficient utilization and meet the exact demand of each item. We optimize all presses concurrently, ensuring the system meets physical constraints and works collectively to minimize waste and interruptions. This approach provides no press is underutilized or overcrowded, enhancing production efficiency. Our methodology significantly departs from traditional 2D bin packing, which typically involves fitting objects into a known number of predefined bins of fixed capacity. In our context, we face the unique challenge of not knowing the size or the number of bins, representing presses, in advance. Additionally, each press can vary in size, requiring a dynamic approach to efficiently manage multiple bins simultaneously. The diagram shown here illustrates the workflow and interplay of our evolutionary search approach. This includes the column generation process where the subproblem and the master problem interact cyclically to refine solutions. The results are then fed into the packing process, which is evaluated and optimized further by the evolution strategy. This cycle continues with the evolution strategy selecting the optimal setups and parameters to feed back into the column generation process, ensuring continuous improvement in our solutions. Column generation is a powerful tool for efficiently solving large-scale linear programming problems. This technique involves two main components: the master problem, which uses continuous variables and is relatively more straightforward, and the subproblem or pricing problem, which uses integer variables and often presents more complexity due to constraints. In our project, we apply column generation to efficiently develop candidate cutting patterns, which can be selected in the packaging process in Glulam production. These patterns are generated to ensure they are potentially helpful, optimize the use of materials and machinery, and minimize waste. In our context, the critical task of column generation is to create a diverse set of viable pattern options that do not overly complicate or increase the computational cost of the subsequent packaging process. The key feature here is the ability to customize the MIP models to meet specific production needs. In the packaging process phase, we take the candidate cutting patterns developed during the column generation and subject them to further optimization using a mixed integer programming model executed in Groby. This MIP model is specifically designed to find the optimal arrangement of this pattern across multiple presses. The primary objectives of this phase are twofold. Firstly, to ensure that the demand of each item is met exactly across all presses. Secondly, we aim to minimize the number of presses used in the production process to enhance overall operational efficiency. Additionally, we strive to reduce any potential waste of materials by ensuring that the placement of patterns within each press is as efficient as possible. This optimization is computationally intensive due to the complexity of variables and constraints involved. Our evolutionary search algorithm optimizes row lengths for generating cutting patterns, which are then integrated into the column generation and 2D packaging process. Row length is a critical parameter, and the number of possible configurations can be vast due to the variability in press sizes. Depending on the search methodology, the ES operates as either a 1 plus 1 ES or a mu plus mu ES. We randomly initialize row lengths to use them to generate cutting patterns. These patterns are employed in the packaging phase, where the evolutionary search selects the optimal row lengths. The evolutionary search dynamically adjusts the row lengths in each generation to minimize waste and improve efficiency. When a new row length does not result in a unique solution, a retry process is initiated up to 100 times to generate a distinct row length. If unsuccessful, the row length is reset according to the initialization procedure. This iterative process ensures continuous improvement and optimal utilization of the presses. Our study used the Gurobi optimizer with 12 CPUs to solve MIP models. We worked with real-world datasets covering 5 different beam depths. The 90mm depth was divided into manageable subsets to balance the total area and minimize distinct orders. We focused on the initial subsets, continuing with partially utilized presses in subsequent subsets to maintain production flow. We targeted 100 generations per run, extending to 200 for the less intensive datasets. The runtime for each packaging MIP model was limited to 20 minutes to avoid excessive computational time, as the packaging phase was a significant bottleneck. Each dataset had 10 independent runs with a maximum wall clock time of 8 hours per run. This slide presents examples of optimized layout configurations for Glulam beam datasets. The figure shows the 115mm beam dataset arrangement across 6 presses. Here we have the 140mm beam dataset arrangement across 9 presses. These visuals demonstrate the efficient utilization of press capacity, though the final presses do not meet the minimum height requirement, rendering them infeasible as currently configured. Our research has led to notable advancement in glulam production efficiency through optimized cutting and packaging strategies, significantly reducing waste and improving resource utilization. This contributes to a more sustainable production process with a positive environmental impact by minimizing material waste. We demonstrated the effective use of column generation and evolutionary strategy, achieving efficient cutting patterns across multiple press configurations. Future improvements could include refining row length selection and implementing pattern pruning strategies to balance pattern diversity against computational demands. Overall, our research offers valuable insights into enhancing operational efficiency and sustainability in the wood industry. The code and data used in this study are available at our GitHub repository. We gratefully acknowledge the Ramnes Research Fund for supporting our research. Special thanks to Limtrevirnet, the factory we used for our case study. Thank you for your attention.